Have you ever wondered why some things in our world only seem to happen in one direction? Well, it turns out there's a reason, and it's all because of a fundamental concept in physics and chemistry called entropy. So let's dive right in.
Think about it. We see this stuff every single day. Ice melts into a puddle. Cream mixes itself into your coffee. Air rushes out of a punctured tire. But have you ever, not once, seen the reverse of that happen on its own?
So what's going on here? Why does the universe seem to be on a one-way street? You're never going to see a puddle of water just spontaneously freeze itself back into a perfect ice cube on a warm day. The answer to this huge cosmic puzzle, this arrow of time, is entropy.
Now, you've probably heard entropy described as just a measure of disorder or randomness. Like a messy room has more entropy than a tidy one. It's a really popular analogy, but honestly, it's also a little bit misleading, and I'm going to show you why.
Okay, let's put that whole disorder idea to the test. Just take a look at these two. Which one would you say looks more disordered?
So on the left, you've got crushed ice. It looks totally chaotic, jumbled up, a real mess, right? And on the right, you have a nice, smooth, uniform glass of water. Now, most people would say the ice is obviously more disordered. But, and here's the big twist, the water actually has higher entropy. See? The whole disorder thing kind of falls apart.
So if it's not about disorder, what on earth is it? Well, the real answer, the much better way to think about it, is probability. And trust me, this is where it gets really, really interesting.
To get our heads around this, let's just build a super simple model, okay? Imagine we have two little solids sitting next to each other. We'll say each one is made of just 6 atomic bonds. Now, think of these bonds as tiny little buckets that can hold energy, and that energy comes in these indivisible little packets called quanta.
And in our little model, the rule is easy. The more energy packets a solid has, the hotter it is. Simple enough, right?
All right, here's a key term we gotta know, microstate. It sounds way more complicated than it is. A microstate is just one specific arrangement of all the energy in the system. It's like taking a single snapshot and seeing exactly which bucket each little energy packet is in at that exact moment.
So let's run a little experiment. Let's say we have a total of 8 units of energy. If the hotter solid, we'll call it solid A, has 6 of them, and the colder one, solid B, has 2, how many different ways, how many different microstates can we arrange that energy? The answer is probably not what you'd guess. It's 9,702. Almost 10,000 different ways to arrange the energy for just that one setup. That's a lot of possibilities.
And here it is. This is the absolute key to understanding everything. If every single one of those microstates is equally likely to happen, then the configurations that have more microstates are just flat out more probable. It's a pure numbers game.
And that is the true definition of entropy. It's not about messiness. It's a direct measure of an energy setup's probability. So low entropy means the energy is concentrated because there are just fewer ways for that to happen. High entropy means the energy is spread out because there are a vastly larger number of ways for it to be arranged. Of course, in the real world, energy isn't static. It's not just sitting still. It's constantly jiggling around, jumping from one bond to another. So our system is always shifting, exploring all those different microstates.
Now check this out. This chart shows us the possible futures for our tiny little system. So there's a 21% chance the energy will spread out even more. That's the most likely outcome. But wait a minute. Look at that last bar. There is an 8% chance that the hot solid will actually get hotter by spontaneously sucking energy out of the cold one. In our little model, that's totally possible.
And that brings up a really obvious question, right? If it's possible for a hot thing to get even hotter in our model, why does it never ever happen in real life? Why doesn't your lukewarm coffee ever just decide to start boiling on its own?
The answer, as it so often is in physics, is all about scale. Our model was tiny. The real world is not.
So let's just scale up our model a little bit. It's still tiny compared to a real object, but instead of 6 bonds, let's say our solids have 6,000 each. And instead of 8 units of energy, let's use 8,000. Now let's see what happens to the probability.
The chance of that hotter object getting even a little bit hotter now drops to, well, that. Look at that number. That is a number so vanishingly small, it's basically impossible to even think about. We are talking about odds that are so ridiculously, astronomically, laughably tiny.
And that right there, that is the big aha moment. For any object you can actually see and touch, with its trillions and trillions of atoms, the odds of energy deciding to concentrate itself instead of spreading out are so absurdly small that it is a statistical impossibility. It just never happens.
So let's be crystal clear about this. There is no mysterious force out there pushing things towards higher entropy. The universe isn't like actively trying to be messy or spread out. And this brings us right back to our original puzzles. Ice melts, cream mixes into your coffee, and air escapes from a tire for one very simple reason. The final states, where the energy is more spread out, are just statistically, overwhelmingly, mind-bogglingly more likely to exist. It's not a force, it's just the universe playing the odds. This constant, undeniable statistical march from less likely states to more likely ones is what gives time its direction. It's that one-way street we talked about. It's the difference between a movie playing forwards and one playing in reverse. And that is why entropy has been so beautifully called time's arrow.
And this leaves us with one final, really profound question to think about. If the entire universe is on this one-way journey toward a state of higher and higher entropy, what does that actually mean for its ultimate fate?